The heart is amazing for many reasons, but one of the cool things that it does is that it has self-excitable fibers that depolarize all by themselves, and then that depolarization, that excitation, spreads through the rest of the heart. And this is what causes, ultimately, the heart muscle to contract. So this is a picture of the conduction system of the heart. You can see we start right here at the sinoatrial node, or the SA node. And this node's nickname is also the pacemaker of the heart. And that's because as these cells depolarize, they are responsible for establishing the fundamental heartbeat. So heart rate is established by the sinoatrial node. Even without influence from the brain or anywhere else, the sinoatrial node will automatically depolarize and fire off impulses that spread through the rest of the conduction system. Now, the brain and the vagus nerve and different aspects of the nervous system can affect heart rate, can increase it or decrease it, but the fundamental heart rate is established here at the sinoatrial node. So, as these cells in the sinoatrial node depolarize, their signal spreads throughout the heart. You can see some of this signal spreads through the right atrium, and the signal is also going to spread across the heart to the left atrium. And this signal actually travels very, very rapidly. There are gap junctions that are present, and so you have very, very fast transmission of the signal. So when we look at the cardiac cycle, you see that the right and the left atria do contract at the same time, and that's because this signal travels very, very rapidly. So it travels to the left side from the sinoatrial node. It also is going to travel down here to the atrioventricular node. If the sinoatrial node is damaged and is no longer producing its own action potentials, it's no longer self-excitatory, the atrioventricular node can take over, but it does depolarize at a slower rate than the sinoatrial node. From the atrioventricular node, the signal will continue down through the interventricular septum down here into the right and left bundle branches. And from there, you see these fibers coming along the right ventricle and along the left ventricle through these Purkinje fibers or the subendocardial conducting network. So as these impulses travel through the conduction system of the heart, you have stimulation of the muscle of the heart, and that's what's going to cause contraction. Contraction of the atria is caused by the signal sent by the sinoatrial node, both the right and the left atrium. And then the right and left ventricles contract as the signal reaches these Purkinje fibers, or the subendocardial conducting network that line the ventricles. But what actually does an action potential coming out of this sinoatrial node actually look like? It's a little bit different than the action potential that you may be familiar with regular neurons. But there are some similarities. So this is a graph showing action potentials that occur at the sinoatrial node. You can see down here on the x-axis you have time in seconds, and the y-axis is showing membrane potential. And so you can see threshold is going to be at negative 40 millivolts right here. And you can see that there's kind of a traditional depolarization as you go up and become more positive, and a repolarization as your membrane potential becomes more negative. So those are some similarities to other kinds of action potentials. What is a little bit different is this pacemaker potential that you see here. You start off pretty far below threshold, and there are some very leaky sodium channels that allow sodium to creep into your nodal cells that are found at the SA node. As sodium, that positive charge, creeps into the cell, it makes the membrane potential more positive as that positive charge comes in. As more and more sodium comes into the cell, very slowly you can see, eventually you'll reach threshold. And once you reach threshold, you get your big depolarization. So that's another similarity to normal action potentials. A difference is that this depolarization is caused by a channel that allows in calcium in addition to sodium. And this happens much more rapidly than our pacemaker potential that we see down here. So you have slow, leaky sodium channels with sodium coming into the cell. Once you reach threshold, it stimulates these calcium-sodium channels, which allow very rapid influx of your positively charged calcium and positively charged sodium, and that leads to the rapid depolarization that you see here. You can see the numbers going more positive. And then you have potassium channels that open. So your calcium and sodium channels close. Your potassium channels open up and sodium leaves the cell. As that positive charge leaves the cell, your membrane potential becomes more negative. So that's why we're going down. And in fact, your potassium channels allow so much potassium in that you dip down below threshold, you actually see some hyperpolarization going on right here. And then potassium channels close and you start the whole process over again. Your leaky sodium channels allow sodium to come into the cell slowly. When enough sodium comes into the cell, that stimulates the opening of your calcium and sodium channels for a rapid depolarization. Your membrane potential becomes very positive. And then potassium channels open. As that positive potassium exits the cell, you have repolarization happen right here. And then hyperpolarization as you dip down below that threshold line. And then, again, you start the whole process over again. So this part from this pacemaker potential from here all the way to here, this would be one heartbeat. So as you have this depolarization that leaves from the SA node and starts moving toward the AV node and down the bundle branches, as this happens in the atria, that's going to cause atrial systole or contraction of the atria. And then as you have repolarization happen, that's going to signal to your muscles to relax. Those muscle cells will go into diastole. And then as this signal continues to travel down all the way to the Purkinje fibers, then you have contraction of the ventricles. And then as repolarization happens, you'll have relaxation of the ventricles. But this, what you see here, this kind of action potential is different than the one that you would look at in the muscle cells. These action potentials are what you would see in the conduction network, and particularly at the SA node.